Morning, everyone. So again, while we are waiting for more people to sign in, if you could turn on your camera, I would encourage you to do so.
How's it going, Professor?
Good so far. How about you? How about yourself?
It's going good. I don't know about so far because I just woke up like 20 minutes ago.
Oh, yeah. That saved some time to commute. That was good. Somehow I don't have my virtual background today. I don't know why. So you have to bear with my boring background here in the office. Okay. Good morning, everyone. All right. Okay, so Monday we talked about, I wanted to talk about more, but we only end up talking about two physics quantities in kinematics. One is, still remember which two? One is to describe where you are, that is a position vector. And then if you have changed your position, the change of the position is displacement, right? Now let's define another two quantity, that is, one is velocity, one is acceleration. So velocity is simply the change of position over time. You can see this motion diagram I'm showing right here. You have a dot change in position from this point, from here to here, and that's delta R naught. From here to here, that's another change in position, right? So every same time interval, the object changes position. So this change of position, the displacement, is happening over this amount of time. So you simply will say the V average is going to be your change of position over time. The displacement over time is your average velocity. Why do we call it the average velocity? Is because you are only looking what's relatively how fast you're going average between, let's say, 1 second and 5 seconds. Between the time interval you're looking at, this is on average how fast you're going, right? You might be go a little bit faster or slower, but this particular definition doesn't really tell us what happened at the moment and instant. It only tell us what's happening on average. So that is your average velocity, is displacement over time. So you can see the difference between velocity and speed, right? Speed is the change of distance, the overall distance over time. So the difference between speed and velocity is this is distance over time, this is change your position over time. So that means, okay, if you here, you're at home, let's say you come to campus, right? And then you come back. So if I'm looking at the overall average speed, right, I just look at the overall distance you traveled. Maybe it's 30 miles overall round trip, for example, and across whatever time you take. Let's say it took an hour and a half to go round trip. So that is your speed. You can get your speed that way. However, if you look at the average velocity, then you realize your displacement is not equal to your distance. You start here and you end up back in the same spot. So that means your displacement is what number? So if you start here, going back here, your displacement is going to be
0.
0. Very good. So which means your average velocity will be 0 because you haven't changed your position at all over this amount of time. But you can see this really just because your average velocity is a vector, right? You have some vector. First, you're driving to campus, your velocity going this way, and then driving back home, your velocity going the other way. So if you look at average velocity, give you an overall 0. So that is the difference between velocity and speed. So we need to be a little bit careful to see the quantity. What do we divide time by? So you can see average velocity really doesn't tell you what's going on, all the situations that may happen between T1 and T2. So that's why we also need to develop another definition for what is going on at this moment. At this moment, at this instant, how fast are you going? Which direction are you going? So that is what we call instantaneous velocity. So here we can do the definition by using the idea of the limit and math is that if you take this 2 point on your trajectory, right, that is happening over delta t amount of time. But if you shrink these 2 points to be very, very close to each other, the distance, the displacement between these 2 points is infinitesimally small, very small. So this point and this point are right next to each other. And so you can see you haven't really changed your speed all that much if you're talking about 2 points right next to each other. So that gives an idea, we can get really close to what's happening at this instant. So that is giving us the instantaneous velocity. So the same delta r over delta t, if we take the limit where delta t goes to 0, and that gives you what is the velocity at that instant, right? And in you can also rewrite this limit when delta t goes to 0 as a derivative of dr over dt. So more generally, we say velocity is simply the derivative of position over time. So this is a very powerful definition. A lot of our kinematics equations will be derived from this equation.
Professor, I have a question.
Yeah.
So when we're referring to the term velocity itself, are we by default referring to instantaneous velocity or average velocity? And
yeah, when we just say velocity, we refer to instantaneous velocity. So when the problem asks you, unless it's specifically asks you what is the average velocity, it is talking about a velocity at an instant.
okay, so it will be specified.
Yeah, it will always tell you which one they want you to calculate.
And then we'll assume that instantaneous velocity, if it just says find the velocity of something, it's just instantaneous.
They might say find the velocity at t equals 0 or t equals 5 seconds. So it is
Okay.
what's the velocity at that second, at that moment.
Okay,
Yeah, very good question. Thank you, Jacob.
thanks.
So velocity is a vector as well as displacement and position, right? When you look at this your derivative time is a scalar, so the vector sign are kept on both sides of the equation. The magnitude, when a lot of times we just refer to the magnitude of velocity, like 30 miles per hour as speed. And in terms of direction is in which direction the object is traveling. So there's a way we can figure out the velocity from the object's path. So given the position, we can figure out what is the direction of velocity. So the idea is coming from the derivative, the math. When you take the derivative of something on a graph, so if you were giving a graph and take the derivative, and that's like taking the slope, because you can see here, v is in the same direction as the change in your position, dr, right? So this is the same direction as dr. And you can see dr, when these two are so close to each other, this is the change in your position, dr. And that's really just like a tangential line across at this point along the trajectory. So for example, if there's a question, I give you, okay, an object follow this curve, this blue path, that's the trajectory it's taking. What is the direction of velocity at this point, P1, and what is the direction of velocity at this point, P2? So given this path, all you need to do simply is to find the slope. That gives you the velocity, and right here you can see this would be the slope at this point, right? This would be the slope at this point, sort of just a line that is tangential to your curve, right? So draw a line that is tangential to your curve, which represents your trajectory of the object, right? Obviously right here at the top is going to be like this. So you probably have seen some of your pre-lecture questions or bridge questions that is doing a giving you one graph and you try to do the other graph. So for the rest of the class later today, we will do a lot of graph analysis, so we can say more about that later. The next thing I wanted to talk about is the very last kinematics quantity before we go ahead and start using them to solve problems. The last quantity is called the acceleration. So you can think of this as an analogy of how we define velocity. Velocity is a rate of change in position. Rate of change, meaning does that change happen in a short amount of time or a lot of time, right? A change in position is delta R over delta T. This is the change in position and it's happening in this much time. So that is the rate of change. So that's how we translate words to math, right? And acceleration is a rate of change in velocity. So using that with the same logic, we will say, okay, acceleration as the rate of change in velocity. So change in velocity, how to represent it in words in math is delta V, right? That is change in velocity and it's happening over in a certain amount of time. That's the rate, delta T. So use the same idea, you can see that if V is delta R over delta T, then A is delta V over delta T. So how, if something is speeding up or slowing down, then how fast is it speeding up or slowing down is described by acceleration. So that's the definition for acceleration. And you can see that if this is happening over some amount of time, you really just have an idea overall, what is your acceleration? You don't really know what is your acceleration at a moment. So delta V over delta T give us average acceleration, right? So this is really a average. But what if we want to know a acceleration at any instant? So instantaneous acceleration, how do we get instantaneous acceleration?
Wouldn't it be the derivative of the velocity over time?
Yeah, it would just simply be the derivative. Very good, thank you. So it would be the same idea. If I take the average, but the average is average happening in a very short amount of time, that is very close to looking at what happened at that moment, right? So if it's T equals 0.0001 second and 0.00015 seconds, this is so small, it's almost telling me what's going on at that instant. So when delta T is equal to 0, is approaching 0, this whole thing using our math knowledge is derivative of dv dt. So that is another very important definition for acceleration. That is dv over dt. So previously you had v as in dr over dt. A is dv over dt. So these two are important, very fundamental definitions. We will later on use them to derive more kinematics equations for us to be able to use and solve problems. So acceleration is also a vector, right? Not only we talk about how fast the velocity is changing, we also wanted to tell people in which direction it is going. So if you're so in our daily language, we will say something is accelerating, meaning that it's speeding up. Sometimes we say it's decelerating, meaning it's slowing down. However, in physics, we will refer to whichever way your acceleration is pointing, we will all call that an acceleration. So either your acceleration is in the same direction as your velocity, which means it will make it continue to speed up, or if your acceleration is opposing velocity, then that object will be slowing down. But in whichever way, we call it the acceleration of the object. So let's look at this question. We can find out the direction of the acceleration by looking at the change in velocity, right? Because acceleration is really delta V over delta T. So giving two velocities, you can see, okay, what is the change? Then you will be able to find the acceleration. So for example, here on the graph, we were given V1 and the arrow pointing this way. So that's your velocity at that moment. And then v2 is your velocity at another instant. And to look at the change, so here I already have laid it out for you, is a red arrow pointing from this one to this one. So how do I get there? How do I know that delta V is this red arrow, but not something else? We have talked about vector addition. So is there any way we can use vector addition to help us here? We want to find delta V, right? Delta V is the change. So if you say how much it changed, use what happened later minus what happened earlier. So that's why we say it's V2 minus V1, because 2 happened later. That's the change. Right, you have, let's say you have $50 and then you had $100. So the change is positive. Use 100 minus 50. So here is V2 minus V1. So I want to be able to figure out in what direction delta V is. I can use vector addition saying, well, whichever quantity that makes V1 plus this quantity equals V2. So if I draw an arrow connecting V1 to V2 this way, right, then I know from head to tail method, the head of V1 is overlapping with the tip of delta V. So that is indeed give me a third vector that is V2. So this shows me this is delta V. So if this is delta V, then A is also delta V. Okay, so A would be approximately in this direction. I want to just walk you through this question. We're not gonna have you vote. So given velocity, the vectors, you can figure out the direction of your acceleration from your velocity vector. So this is what this question is trying to get at. Okay, so now I want to switch gears to talk about different graphs, as we were saying something like that earlier. One way to analyze motion is to, we draw pictures. Motion diagram is a way like a picture. Another way is to look at graphs. Graphs are another way to represent different functions. So you can draw 3 different graphs here. You can draw how position changed with respect to time, how velocity changed with respect to time, and how does acceleration change with respect to time. So, okay, first of all, let's start with how does position change over time. This is your motion diagram. This is me walking across the room. This is my position, and also I have my coordinates labeled 1 meter, 2 meters, 3, 4, and 5 meters. So let's look at my position. How does it change over time? At t equals 0, I'm at 0 meters. T equals 1, I'm at 1.1 meters. T equals 2, I'm at a location of 2.2 meters. And T equals 3, 2.3, and T equals 4, 4.4. We can draw this on the XT graph, right? You can connect the dots. So you will do this quite a bit in your lab. So 0, 0 is this point. T equals 1, this is 1.1 is this point. T equals 2, 2.2 is this point. So you draw all those points that represent my location and at a specific time. So you will have your position time graph. So it looks like all the points are perfectly on the line. You simply draw a line showing this is how my position changed over time. So if I didn't tell you anything else, and I just give you this graph, right? You only have information about my motion that is represented by a graph. What can you conclude from this graph? You will say you're walking with some kind of speed or velocity. What does this graph tell you how I move? Constant velocity, thank you, and Gemina. I'm moving with a constant velocity. because you can see that the intervals, the change in you have equal amount of change, right, in position, which is represented by the y axis in equal amount of time. So every 1 second, you will change your position by exactly the same. So that's a constant velocity. You can also read this by looking, well, it has a constant, the slope does not change. This is one straight line, it has one slope, right? So slope represents velocity. So if you have a constant slope, that means a constant velocity. So here, from the graph, you are communicating with others that the person is moving with a constant velocity. So that's all the information you can read from the graph. You know how to calculate slopes. That's the rise over run, right? The change in your position is delta x, the change over time is delta t. So notice that when you are giving a line, you can take any 2 points on the line to calculate your slope. It does not have to be the points that you originally used to graph your picture. So you can take these 2 points. You can take any 2 points on the graph. It doesn't matter. It will give you the same slope anyway, right? So take whichever 2 points that seems most convenient for you and calculate the rise over run, and you get your slope. So if that's a positive slope, meaning your velocity is positive. If you have a negative slope, that tells you a negative velocity. So if you were to draw this and convert this picture into a velocity graph, then you will have to draw a velocity with that. So for example, this slope is 1.1 meters per second, right? It's a constant velocity. So what I would do, okay, so this is 1.1 meters per second, and it simply just remain the same velocity throughout, right? So this and this are communicating the same information. This is a question from your pre-lecture. Should have seen this already. I want to go through this just to see how the knowledge we just said applies here. For example, if you are giving a position time graph, plot x versus t, and that is represented by this red parabola. So we want to see which one of these statements is true regarding the velocities, right? So velocity at t equals 0 seconds, or t equals 1 second, 3 seconds, and so on. So you can see, you can draw a few different tangential lines at different locations of your position time graph to sort of describe to yourself how does the velocity change. So on the left-hand side, I'm drawing a blue line as a tangential line of exactly the velocity at t equals 1 second. So you notice that there is a negative slope, right? And I see that if I move to the right-hand side of the graph, for example, if I'm drawing a t equals 3 seconds, I get a positive slope. T equals 4 seconds, I also got a positive slope. So what does that tell you about the velocities? What does that tell you about the motion of this object? The fact the slope has reversed signs from negative to positive. What does that tell you?
The object like turned around.
Turn around, very good. It went from one direction and going the other direction, and therefore it reversed the sign. Very good. Also, you can see that it makes sense because before you can turn around, your velocity, you have to slow down, right? So at some point, velocity here is 0, right? 0 velocity. And then you turn around. And also, after you turn around, what do you notice about your velocity? Are you going faster and faster over time or slower and slower over time? Faster, yes, thank you. Jose and Elaine, and all of the answers that you were giving me. It goes faster and faster over time because you can see the slope getting steeper and steeper, right? This is much more steep than the other one. All right, so we know what the right answer is. The velocity is greater than 0 at t equals 3 and 4 seconds, right? We got positive slope at both of those seconds. In fact, we read much more information than just this one statement, but that's all it's asking us to select. So D is correct. Very good. All right. Okay, so this one I do want to go ahead and give it to you guys to answer. So giving 3 different particles that are represented by 3 different lines. This is a position over time graph. So can you rank the speeds of these particles? So think about this. They're asking about speed and not the velocity. So whichever way the particle is going is not of our concern. So this one, I will just go ahead and let you put in your vote here. Take a minute or 2 to think about this, and whenever you're ready, you can put in your vote here. All right. Let's go for 10 more seconds. If you haven't put in your vote already, please do so. All right, any last minute vote? Okay, I'm gonna go ahead and close this so we can take a look at this together. All right, so here is a distribution of different answers. All right, it seems like we do have a majority of the vote on B, and we also quite equally split between D and E. So there are 3 different ones. We can try to compare maybe the consensus one, right? You do have the consensus between B and D that A and B have the same speed. So do we all agree with that, that A and B have the same speed from the graph?
Yes.
How can we tell?
Yeah.
How do we know?
They look to be parallel lines, so that means their slope's going to be the same at every point.
Yes, thank you. They are parallel lines. They have the same slope. Very good. So you haven't changed how much it tilts, right? Haven't moved it this way or this way. It's like parallel, so same slope. Very good. So we know A and B have the same velocity, also same speed. Now the next question is just to compare to C now. That seems to be where the difference is from. So looking at C and A and B, is C more steep or less steep than A and B?
It's more speed.
It's more steep, right? If it's hard to, if you're trying to answer the questions of which one has a bigger slope, if that is difficult, try to think about how steep it is. I think that you can take advantage of your intuition that way. Think about if you're like sliding down, right? Sitting here versus if you're sitting here, right? Which one you think is much more steep? So I think that's a little bit more obvious from the graph to see that C is much more steep. Get rid of the little pictures. I don't want to people get confused on why they draw a person there. So C is more steep. C does have a bigger, in terms of the absolute value of the slope, it has a bigger slope, but it's also negative, right? So we're simply saying object C is moving in the opposite direction of B. But we're not really caring about the directions. We want to know the speed. So the speed showing that C is faster. C is moving with a bigger velocity and it is faster. So the answer is B. B is the correct answer. Very good. Yes, so someone asked, so is speed referring to the absolute value of the rate of change? Not quite. You can see that speed is really the overall distance over time. So when you are not, so for example, when I say you go from home to Cal Poly and come back to home, right? If you're looking at just one way, home to Cal Poly, you can say my absolute value of your displacement. Now also if you're going a straight line, so this is a lot included. If you're going from home to Cal Poly in a straight line, that it's impossible. Imagine an ideal world you can. Then yes, then your delta R is exactly the same as your distance. So that make your speed is the absolute value of the rate of change of your position. However, in real life, these are different, right? You if you go from home to Cal Poly and then you can also go back to home, then you cannot say your speed is 0. You do have an overall average speed, but your velocity, but your displacement is 0. So your average velocity is 0. That's why these two are different. But if you're looking at simply what is happening at an instant, momentarily, instantaneously, then yes, if you're looking at an instant, then your speed, your instant speed is the absolute value of your instant velocity. So it really depends on what the question is asking. Does that make sense? Okay, all right. So moving on to look at the second kind of graph. We said we did the velocity, we did the position over time graph. Now we do the velocity over time graph, right? So you can see that if your position time graph is a straight line, that shows your velocity is a constant velocity, which make it flat line, right? Going straight across, it's flat. So these two graphs are equivalent to each other, right? They're communicating with you with the exact same information. From this graph, you read your slope is 100/10. That's 10 meters per second, right? So you're just going to draw a 10 here, and that's go all the way across, meaning that the velocity does not change over time. So these two are equivalent to each other. However, if your xt graph is not a straight line, but a curve instead, then you can see that, oh, I can also tell about the velocity information from this graph is because that the slope is actually increasing over time, right? So if I draw a little slope right here, is this, that is not as steep as this, and it's not as steep as my slope at a later second, right? So here you can say my slope is increasing, which means my velocity should not be a flat line. It should show an increase, so be going up overall. It turned out if this is a perfectly parabola, then your velocity would be a perfect line, showing that it's increasing, right? Going up and up over time. In fact, the first kind of graph represents constant velocity. The second type of graph represents non-constant velocity. And in particular, this one represents a constant acceleration type of motion because your velocity is not constant, but it's increasing in the linear way, right? This is a line, this is linear. So that is actually a constant acceleration. We will talk about how we know that when we do kinematics equations. We would derive our equations, but at this point, we will just leave it as that. It's going to be a linear, and your x graph is going to be a parabola.
Would acceleration ever not be constant in this class, or is it always like majority of the time it will be constant?
Yeah, as far as this class goes, our acceleration will be constant. We will not derive kinematic equation for a non-constant acceleration. We'll get too complicated. Yeah. So constant acceleration is the type of problems we often encounter in this class.
Oh, thank you.
Okay. Okay. All right. Moving on to another question. Here we have a train that is moving along a straight track. We are giving you a position versus time graph. I don't know if you see it clearly, but it's represented by this black line here. I'm gonna make it a little bit more obvious. This is your position time. This is your position time graph. So what does that tell you about the train in terms of the motion of the train? All right. Let's see.
It slowed down and stopped.
Oh, sure. I'm just gonna go ahead and then
Sorry.
put in your votes. I clicked the wrong thing and didn't show up at first, but now it's showing up now. Okay, take another 10 seconds. If you haven't voted already, please put in your vote. All right, let me go ahead and close the vote. We can take a look at the results. Quite even between B and D. whether we all agree it slows down part of the time, but does it speed up part of the time, or does it slowing down the whole time? So how can we tell from the position time graph? What do you guys think? Anybody would like to share their thoughts?
Do you look at the whole graph? Do you look at the graph as a whole and then compare the time as time goes on? You base it off of that. So for me, I put that it slowed down the whole time. My reasoning also is if it were to speed up, the start of the graph would be flat, and then it would rise up, and then it would taper off, as in this graph.
I see. So you're saying if it does have a sort of a speeding up process, sort of your graph curve will kind of flip, right?
Yeah.
So something like this.
Yes, exactly.
Indicate. Okay. Yes, very good. Thank you for your thoughts, Jacob. So we are using the technique of drawing tangential lines on position time graph to figure out the slope, and how is slope bigger or smaller, indicating if it's speeding up or slowing down, right? Is slope getting bigger or getting smaller? So you can see there are 3 different points indicated on this graph, right? A point kind of in the beginning, a point right here, somewhere in the middle, and the point toward the end of the motion. So this is your slope at the beginning. Okay, and this is your slope at a later time, as your slope at another later time. So you can see that the slope is going from this to this to this. So does that tell you the slope is getting less and less steep over time? Does that look clear from the graph? So if you agree that the slope is getting less and less over time, then you should also agree that the speed is getting smaller and smaller over time, right? So it must be slowing down the whole time. If it does have a speed up and slowing down process, then the curve would not be smooth like that. It will be, you'll have something like this or this. So this is speeding up. And here, this is slowing down.
Wait, speeding up or slowing down also refers to acceleration, right?
And speeding up and slowing down refers to, okay, if your speed changes, you definitely do have an acceleration. So speeding up saying that your velocity is increasing, slowing down meaning your velocity is decreasing. So that definitely tells you the acceleration is either in the same direction as your velocity or is opposing your velocity. Think about like you're giving your car a push in the same way that it's already going, or if you're dragging your car behind so that it slows down. Is that what you were asking?
Yeah, I was just wondering, yeah, if like speeding up or slowing down, it's like changing velocity.
Yes, so that does tell you there's definitely an acceleration at play. Yes, yes. Okay, so this one, B is the correct answer. All right, so now let's look at something maybe just slightly more complicated, but I think we, with our technique, we should be able to answer this. Here, we do it in the reverse order. We give you a velocity time graph, and then you find the displacement over time graph, the position over time graph. That is related to the same motion as the velocity graph. So this one we could benefit from using a little discussion. So I will go ahead and let you enter the breakout rooms and for a couple of minutes, and then when you come back, you could vote. All right, so once you see an invitation accepted, but before you go, remember to take a snapshot of this screen so that you know what the problem is, okay? So take your screenshot and then you can enter the breakout rooms. All right, so people have already come back from their breakout rooms. Please go ahead and enter your vote. Could either be your own thought, it could be same or different as what you discussed as a group. Okay, let's go for another 10 seconds. If you haven't put in your vote, please do so. Okay, I'm gonna go ahead and close this. All right. Anybody would like to share their thoughts with us, how they approach this question?
So how I did it
Okay.
was that I remember from Calc 1 that so since displacement, when you take the derivative of the graph of displacement, you get velocity.
Mhm.
But conversely, it's also true that if you take the integral of velocity, then you'll get displacement.
Okay.
So because velocity is a linear function,
Mhm.
I know that if we take the integral, we're going to get a quadratic equation.
Okay.
So then it'll look like a parabola. So that means it can't be C.
Okay. Good.
And we know that at t equals 0, velocity changes from positive to negative,
Okay.
right? So then we know A and B both have that because they have a they have a change in direction at t equals 0
Mhm.
because of the parabola, like that's where its vertex is.
Okay.
So we know that helps further verify that it could be either A or B. But we know before t equals 0, velocity is positive and the slopes of A are positive before t equals 0, and after they're negative. So then that also lines up with A. So that's why I chose A.
Oh, yes, very good one. I do like the thought process very much. On the left-hand side of A, if you draw a slope, that's a positive slope that's consistent with a positive velocity. On the right-hand side, it's a negative slope, right? And that's consistent with a negative velocity over here. Very good. So the answer would be A. Excellent. Yes, so that's our velocity over time graph. Next class, we will continue to discuss how do we read acceleration from the velocity time graph. Very similar to how we did velocity from the position time graph. All right, I'll see you guys on Friday. Have a good rest of the week. And
Thank you, Professor.
Thank you, Professor.
Thank you. Thank you,
Hey,
Professor.
Professor.
don't forget to do the achieve homeworks.
So Professor, the only homework then is like the things on the achieve screen, right? That's it.
Yes. Yes, you said you did you said you emailed me earlier, you added to the class later?
Add to what?
Was that you? Oh,
I sent you an email about something about the grading policy, like
Okay.
about on Canvas that I had some suggestions, but that's all I've emailed you about.
yeah, the only homework that's the pre-lecture and homework they're all on achieve, other than that pre assessment, which is the extra credit that was on Canvas, but
Yeah.
I've already done that. That's already closed.
Yeah.
Okay. Yeah.
Cool. Thank you.
Thank you.
Have a good day.
Thank you. You too.
I just signed up for the class like last night. So is there any way I'm going to be able to do that pre-assessment thing or
Yes, I will make sure to give you access to that.
okay, cool.
I'll email it to you. You did email me, right, this morning?
I don't think so. No. I was going to email you though, or talk to you after the class.
Okay, give me 1 second. I want to write your name down so I can give you access.
Okay.
Um,
So with the pre-assessment, like what is it?
oh, it's not graded for correctness, even though you do see a score. That's just really for my information. want to see how students are doing overall. So just do it to the best of your knowledge. Do not Google answers. There's no need to Google answers. And there's 30, it's just 30 questions, and you get 1% added to your final grade.
Okay, cool.
Okay, I'm not seeing, okay, Spencer, right?
Yeah.
Okay, let me write it down. So you need pre-assessment. Yes, and then log into Canvas as soon as you can, and you can do the Achieve homework. For pre-lectures, since people are still adding and dropping, I'm not going to count the pre-lectures until things are settled. So don't worry too much about it.
Okay.
And Jonathan, you are the one who emailed me, is that right?
Yes,
Okay, do
I
you
was-
have questions?
I was just going to kind of ask similar I'm not sure when Canvas is going to update. I was just going to ask about kind of getting access to the homework assignment and pre-assessment.
Yes, so I will do the same thing. I will give you the chance to do the pre-assessment, which is an extra credit. And again, as soon as you have Canvas, you could do that. Also, you can click the Achieve. It's under Macmillan Learning. That's on your menu. And then click it, it will direct you to Achieve right away. So I will do the same thing for pre-assessment. It may take Canvas 24 hours to be updated.
Okay,
Okay.
thank you.
Okay. All right. I'll see you guys on Friday then.
Thank
Have
you.
a good
Bye.
one.
Have a good one. Yes.
Professor Ryan, I wanted to know if you will be doing office hours today because I saw it was Mondays and Wednesdays.
Yes. Also, if you want to talk, if you don't, well, I post my videos online, so you probably don't want to. If you don't want me to post, we can talk later. Otherwise, I do have some time now, whichever you prefer.
Okay, well, honestly, I was just gonna ask you, I'm still a little bit confused on the relationship between displacement and velocity. So I wanted to know if you can kind of a little bit like, kind of guide me a little bit better.
Yeah, of course. Difference between displacement and velocity, you said?
Yeah, because I know that acceleration is when there's a change in velocity, correct? So like change in direction, I mean, right? When you're going,
yes. So
I'm not mistaken.
difference between displacement and velocity is simply velocity is displacement over time. You see this over here in my definition? Sorry, not this one. Let's go over to my definition. So you know what displacement is, a change of position. It's a arrow pointing from where you were originally to where you are later. So a direct arrow pointing from initial point to the final point. And you have changed your position over time, over some amount of time. So use that displacement divided by time is your velocity. Does that answer your question?
Yeah, so then can there be negative displacement or that
Yes.
was one of my
Yeah,
primary
there could
concerns.
absolutely be negative displacement. It all depends on where your positive direction would be. So if you say, I want to define to the right as a positive direction, that's up to you. And then you have gone from here, initial, to a final point. So you have gone this way. And let's say that is -2 miles, for example, right? So that will say your displacement is -2 miles. because it's negative, right? It's in a negative x direction. So it's opposing whatever positive you have chosen to be. This showing is pointing to the negative x direction, though that's pointing to the left, right? So if that happened over in the amount of half an hour, I'm just randomly throwing out there. So your average velocity is your change in your position, which is your displacement over time, is -2 miles in half an hour, which will be -4 miles per hour in the negative x directions, right? So you're going this way. Velocity is this way. You're going to the left-hand side. Does that make sense?
Yeah. Okay. That makes much more sense.
Yeah.
All right. Well, thank you so much. I appreciate it.
Of course. And this is just the average, right? If you want to know instantaneous, what's happening in the instant, this becomes derivative.
Oh, right.
Okay.
Because
okay, you go faster or slower, and averages tell you on average what's going on, and instant tell you, oh, in this second I'm going 4 miles per hour, next second I'm going 5. Then you know what's happening at every moment, right?
Yeah, right. And then on a graph, when you're trying to on a graph that portrays position, I saw that for the example, for instance, you know how we read it as in terms of positive and negative, in terms of positive being increasing and the negative being decreasing. But then when it came to the derivative graph, I mean the antiderivative graph, which was the parabola, we read it in terms of increasing and decreasing. So I kind of wanted to ask, like, kind of how do you know when you read it in terms of like increasing, decreasing, or like positive, negative, if that makes sense?
You mean this one, right?
Yeah.
Yeah.
So you know how we read it like positive, negative, and then increasing, decreasing?
Kind of. Okay, so you can read both. You can always read both from a graph. Which one do you read, or do you need to read both? Depends on what the question is asking. Here we only read positive and negative because that is already enough for us to pick the right answer. We can also read the increasing, decreasing information. So for example, here, velocity is positive, and is it increasing or decreasing as it go here? Is it increasing or decreasing?
Decreasing.
Decreasing, because it's go from a positive value and going down, going down to 0. So it's decreasing, meaning that if you were to use that bit of the information, you would say the slope should be decreasing. The slope should be getting less and less steep, right? So if you were to try to see if that makes sense, you say, okay, this is a slope. Not only is positive, it is also decreasing.
Increasing.
Right? Can you see that the slope is decreasing over time? So because it start out here, it gets less steep and less steep over time, right?
Approaching like a constant and then decreasing. Oh, okay.
So we didn't do the increasing, decreasing because we already used positive, negative to figure out the right answer. It's already enough to figure out what the correct answer is. And the problem did not ask us about speeding up or slowing down. This one is asking, is it speeding up or slowing down? So we have to figure out the slope. Is it increasing or decreasing, right? So if this question only asks you, is the velocity positive? Then you would say, oh, the slope is positive. Then you would not care about whether it's increasing or decreasing. So it all depends on what the question is asking you.
Okay. Okay. Okay.
Yeah, but that's a great question. You do have that information from the graph. It's just that we did not have to use it for this particular problem.
Right. Okay. Well, yeah, thank you so much. That was pretty much it.
Of course. Thank you. Thank you for asking.
Thank you. Take
All right.
take
I'll
care.
See you on Friday.
See you.
Bye bye.